Hey everyone, thanks for the introduction. Yes, I'll be presenting about the general theory of liquidity provision for automated market makers. I'm an undergrad at CU Boulder. This is joint work with Roth Frangillo and Manisha Papirati-Gary. Roth is faculty and Manisha is a PhD student at CU. So in 2003, Hansen introduced automated market makers to solve thin market problems in prediction markets. And for the last 20 years, we've been kind of grappling with the question of how do we best design these? So AMMs are always willing to offer a price for any bundle of assets. So if a trader wants to make a trade, an AMM will let them do it. Ideally, AMM should also ensure that prices are stable and will quantify the degree of this price stability with liquidity. And historically, market creators both fostered this trade of assets, but they also bore the risk of providing the liquidity to keep the prices stable. And when I say providing liquidity, this is in the sense of having the assets on hand to make sure that prices are stable when traders make trades. And now in the DeFi world, AMMs have been used as a way to trade assets on chain. And we see this new interface here and a decoupling roles of sorts. So now the market creator could outsource the provision of liquidity to external liquidity providers. So the setup is that liquidity providers can withdraw or provide assets into the liquidity pool, and then the AMM draws from the liquidity pool, and then traders will buy and sell directly from the AMMs. And so LPs or liquidity providers are compensated for taking on the risk of providing liquidity by depositing these assets by getting a cut of fees skimmed off of trades. And when I say taking on risk, this risk is in the form of, well, instead of providing liquidity, I could possibly be trading these assets to maybe get a better profit. So that's the risk that they're taking on. And so when we consider the current state of what the design space of liquidity provisioning protocols, let's consider Uniswap v3. So in Uniswap v3, LPs allocate liquidity by depositing assets in these discrete buckets that partition the price space. And so this is kind of how that looks. Our price space is from 0 to 1. And in this case, our bucketing intervals are partition that into 10 or into 0.1 wide slices. And, you know, liquidity providers can deposit assets or allocate liquidity across this price space however they'd like, but usually it's centered around the price of the assets, and that's kind of around here. So how do we actually implement Uniswap v3? So there are two kind of fundamental parts of this. One is if a liquidity provider wanted to allocate some liquidity across some bucket, how much of each asset would they have to provide to the market to make that happen? And that's kind of encapsulated in this modify liquidity subroutine here. The second part is when a trader wants to make some trade, what are the things that need to happen for that to occur? And so that happens in this execute trade, and it essentially boils down to this check that the AMM computes. And let's be honest, this is a bit scary, especially this check. So when we consider what it means to expand this design space of LP protocols, there's two natural questions. So one is, what's a principled way to come up with liquidity provisioning protocols like this? And the second question is, how can we fully characterize the design space of liquidity provisioning protocols? And a possible answer within our framework that I'll talk about is we can think about liquidity provisioning as LPs running their own automated market makers operating in parallel. And I'll get to kind of what that means. And so for the rest of this talk, I'll introduce our new framework. I'll give some examples, and then I'll recap at the end. So in traditional markets, liquidity is provided by multiple market makers quoting prices in parallel. And what this does is it narrows the spread of buy and sell prices And this leads to price stability. So if you have multiple market makers giving prices for certain trades, these will converge to a certain price. And so when a trade is made, the price shouldn't jump too drastically. And so a natural analog here from going from traditional markets to AMMs, what would running constant function market makers phi1 through phi n in parallel look like? And we claim that this is equivalent to having one CFMM with phi being the infemal convolution, and that captures this running in parallel. And I'll go more in depth as to what this looks like. This slide is kind of like an overview of the next few things to come. So from this idea of running CFMMs in parallel, we actually get a nice maximally flexible liquidity provisioning protocol. So the parts are, each LP chooses and modifies their own CFMM, phi I, arbitrarily. And then the aggregate market maker uses the infemal convolution to kind of emulate the LP's choices of CFMMs operating together. And it turns out that we can recover existing protocols like Uniswap v2 and v3 as special cases in this context. And the general protocol is quote unquote reasonable for any reasonable phi. So as a background for constant function market makers, a CFMM will maintain a reserve vector X in Rn and a convex potential function. And the trades R in Rn that are available are those satisfying this phi of X plus R equals phi of X. And then after a trade happens, the reserves get updated. And just as a note, in the literature, phi is usually concave. Just for the purposes of this talk, think of the negation as being convex, and that's what we'll use. And this allows us to use some facts from convex analysis. And so in Uniswap v2, which is familiar, we have this for our phi of X, and then we have this reserve curve. So at any state in the market's evolution, the amount of reserves will always be on this curve if we plot them. So for our main results, first I'll define the infemal convolution. It's this expression, but you can really just think of it as being kind of a conjugate operator of just addition in this kind of convex conjugate space. And so we claim that all existing liquidity provisioning protocols correspond to an aggregate CFMM, with phi being the infemal convolution of these constituent phi I functions, and phi I is the CFMM that LPI chooses. And we can use this idea to create new protocols. So in existing protocols like Uniswap, LPs are actually constrained to a certain class of phi I functions that they can choose. And we ask if we can generalize this to a broader and more richer class of functions. And it turns out we can. And it turns out that any choice of convex phi 1 through phi n corresponds to a reasonable liquidity provisioning protocol. And this protocol is as follows. Each LP chooses and modifies their CFMM phi I arbitrarily. And then when they do this, the AMM requests assets such that the aggregate reserves are non-negative. So this is kind of goes back to when I'm allocating liquidity, how much do I have to pay to the market maker or deposit to the market maker to make this happen? And so the aggregate market maker uses this infemal convolution again to emulate these choices of CFMMs operating in parallel. And the valid trades are exactly those that are characterized by this aggregate potential phi. And is this reasonable? Well, we'll show that this actually corresponds to a more literal translation of what it means for CFMMs to run in parallel. And liquidity adds, and I'll talk more about what that means in the next few slides. So a more literal translation of what it means to run CFMMs in parallel is if we let CFMMI have a potential function phi I, if traders want to make a net trade R with the CFMM, what we could think of this is making net trades Ri with each CFMM phi I. So if I want to make a net trade R at the end, what I have to do if we're thinking of CFMMs operating in parallel is I'll actually make trades Ri with each CFMM. And of course, rational traders want to trade at the best prices offered. And it turns out that trading directly with this aggregate CFMM does exactly that. It recovers the optimal trade split. And computing this optimal trade split under the hood, which our infemal convolution does, it allows traders not having to choose which CFMMs to trade with for the best prices. So instead of doing all this, traders can actually just trade with the aggregate CFMMs in the valid trade circuit. And two other reasonable interpretations or reasonable implementations or translations of what it means for CFMMs to run in parallel are equivalent, as mentioned in our paper. And so again, if we let phi being our aggregate potential function, let's just suppose for intuition that the Hessian of phi is positive definite. Again, liquidity is a measure of how insensitive prices are while trades occur. So at a price P equaling the gradient of phi evaluated at X, we can define this liquidity function, L of P, as the inverse Hessian of phi evaluated at X. And because L is positive definite, we can say that L is equal to the Hessian of some psi for a convex psi. And this is actually a special case of convex conjugate duality. And by results in convex analysis, the convex conjugate of an infemal convolution is the sum of the convex conjugates. And so with our liquidity functions being the Hessian of phi star, the total liquidity is the sum of the liquidity from each LP. And this is obviously something that we want. So now I'll talk about some examples. And there's two types of examples that I'd like to talk about. One helps us consider and understand existing protocols more deeply. And then we can also use this framework to create new protocols entirely. So remember Uniswap v3's buckets? Well, what if we wanted to generalize them? So let's say we're using the bucketing mechanism where we have something like this, but we want to use any reserve curve. What's stopping us? So one of the key questions that we have to answer is if an LP wanted to deposit liquidity in a certain bucket, AJ, BJ, how much of each asset would they have to provide, given that the current price was P? And it turns out, for Uniswap, we already have this. But for a reserve curve inspired by the logarithmic market scoring rule, we have something that looks like this. And for a reserve curve inspired by the Breyer score, we have something like this. So how did we get this? Turns out there are some technical details involving the duality between reserve curves and scoring rules. And we can do this process. We can extend the bucketing mechanism for an arbitrary reserve curve and come up with these vectors. Bucketing, though, requires LPs to discretize their liquidity allocations. Maybe for more expressiveness, we can try soft buckets that kind of fade in and out of a target price. So instead of having discrete buckets where liquidity drops off from something to zero, we can have kind of a smoother allocation. So consider a triangular function, Tj of P. J is where the triangle is centered, and it looks like a triangle. What we can do is we can weight liquidity functions over soft bucket J, with Lj of P being the multiplication of L, the triangular function, as a function of P. And this gives us something similar to bucketing, but with more expressiveness. Bucketing, though, also requires us to keep track of several parameters. And so a note is that operations involving polynomials are efficient, and also polynomials can approximate most functions. So if we allow liquidity providers to choose polynomial functions L of degree K, this could allow expressiveness like bucketing, But now we only have k parameters to manage. And this may be especially promising in the off-chain setting where the cost of inverting polynomials is not as much of an issue as it might be in the on-chain setting. So to recap, thinking about LPs running CFMMs operating in parallel gives us a nice way to think about liquidity provisioning. And with this framework, we can both understand existing protocols more deeply, but we can also capture all conceivable protocols and innovate and create new things. So in the future, what we'd like to do is wrestle with hiccups that arise from more than two assets. So there are some issues with directional liquidity, with the fact that liquidity is really a Hessian matrix. Also, trading fees in the multidimensional case may not be budget balanced. We'd also like to use this framework to create new protocols with considerations like just-in-time behavior and permanent loss and other considerations that might matter to liquidity providers. And we'd love to hear your suggestions on this. Thank you so much. And yeah, I'm happy to take questions.